Now this is a speech that I've actually wanted to do for a little while, because in sixth form I did something called the Extended Project, which was basically an extra AS. What we had to do was that we had to come up with our own project and develop it over the course of many months, and then give a final presentation on it, and then we get marked accordingly with how well we developed. I chose to research something that has always interested me, which is time travel. Always been very interested in the idea of being able to manipulate time. Not quite in the Doctor Who sense or anything like that, but just simply being able to control my passage through it. And after probably about 6 months of research, I managed to learn a fair bit about this. So I'm going to start off with asking a question. My first question to you, which I want you to answer, what time is it? Go on, tell me, what time is it?
7:22.
7:22, that sounds so bored. What's only 7:22?
7:25.
7:25, right. Okay. To be honest, I can guarantee that whatever time you told me would probably have been wrong. But probably not for the reason that you... Sorry, I don't mean to shoot you down quite like that.
Yeah, you fucking did. That's why you asked the question.
Yeah, well, actually. What can I say? I have a bit of an ulterior motive going on. Now, the thing is that whatever you said would probably have been completely wrong. And throughout the course of this speech, I'm going to explain why. Because the idea of a question that is, what time is it now, makes no sense. Because now doesn't make sense as a concept, which I'll go into later. A better question to ask can be divided into 3 things. 3 questions. What time is it here? What time is it there? And how old is the universe? Now, my original version of this speech was an hour and a half long. I'm not going to do an hour and a half of this. Don't worry, I'm going to try and make it as concise as I can. But hopefully, without missing any of the most important concepts. Also, because time travel is quite very much a physical and mathematical concept, I am going to try and do it with as few equations as possible. So there's no need to worry about that. So before we can answer the question, what time is it now? What time is it here? What time is it there? How old is the universe? We have to actually know what time is. What does it actually mean? A fundamental description of it is that time is an hour, aptly called the hour of time. And there are 7 ways to express this. Thermodynamic hour of time is the first one, which considers entropy, which just means disorder. If you have a mug on a table, and you knock the mug off of the table, it will shatter on the floor. It's gone from an ordered state, as one solid mass as a mug, to a disordered state, shattered on the ground. Entropy has therefore increased with time. This happens naturally in the universe because everything is moving away from everything else. That's a very fundamental point of physics. Arguably, you could say that stars are forming, planets are forming, and so the entropy is actually going down because things are going from lots of dust particles into small solid masses. But this is just a small statistical anomaly, for lack of a better term, because on average the whole universe is getting more and more disordered. Second hour of time is the cosmological hour of time, which simply says the universe is expanding, therefore time is going forwards. 3 ideas that exist about the universe are these. The universe will keep on expanding. So we had the Big Bang 13.7 billion-ish years ago, and the universe is now expanding from a central point and will continue to expand forever. Second idea is that the Big Bang happened, the universe expands and then reaches a sort of a saturation point. It stops getting bigger and just stays there. Theoretically, this would imply that the arrow completely stops. There is no arrow of time. And the third idea is called the Big Crunch. We have the Big Bang, where the universe starts from a single point, a singularity, becomes as massive as it does, and then starts to shrink back to the point before the Big Bang. It's called the Big Crunch. Theoretically, that says that time will then go backwards, because the cosmological arrow of time is now pointing in the other direction. Okay? The third one, which is the only other one we will really consider, because the others are quite complicated, is the psychological arrow of time. You remember the mug? Fell on the ground and shattered. You remember it being in an ordered state, and then you saw it smashed. Psychological arrow of time purely says that we remember the past and not the future. It's that straightforward. The other 4 arrows of time, just go over them quickly, are the radial arrow of time. So if you throw a pebble into a pond, you'll see the waves spread outwards. The causal arrow of time, which is simply cause and effect. You know, I throw this up in the air, it'll come back and land in my hand. The weak arrow of time, which is to do with intermolecular forces, and the quantum arrow of time, which is the idea of wave functions collapsing. But like I said, those are unnecessarily complicated for what we're talking about here. From this, I'm now going to go into explaining about how it's possible to travel forwards in time. Now, this may initially not sound very interesting at all. I mean, we're travelling forwards in time at the moment, aren't we? Seconds just passed, another second just passed. We're carrying on forward at a nice steady rate. That's fair enough. But what if we wanted to visit the far future without having to wait 20 years? What if we want to see 20 years in 2 years? 2 ideas, and you're going to get a little bit scared from these words, involve general relativity and special relativity. Now, normally when people hear that, they will of course get quite worried. Relativity is meant to be quite a complicated concept. But qualitatively, they're really not. They're quite straightforward, if we ignore the equations, obviously. I had a whole course of this in first year, and the idea is fine. The actual equations are quite tough. General and special relativity. General can be summed up quite succinctly. More gravity, slower time. It's that simple. If you think about a black hole, we've all heard of black holes, extremely dense lumps of matter, which have such a great gravitational force, not even light can escape from it. If you travel closer to a black hole, you will experience time a lot slower than the outside world. For you, 10 minutes could pass as you're near to the black hole, but further away, 30 minutes could pass. It's quite an interesting idea. Unfortunately, we can't actually test this because we can't get anywhere near to a black hole. But we can actually see this in day-to-day life almost. The reason GPS works is because of general relativity. For every 400 years, I believe it is, that passes on Earth, 400 years and 1 microsecond passes for a satellite. No, sorry, the other way around. For every 400 years that pass for a satellite, 400 years and 1 microsecond pass on Earth. Now that doesn't sound like very much, but when you're talking about such great distances as these, and we're trying to direct one tiny little car in pinpoint accuracy along a road, then it becomes a lot more important. The fact that the clock on the little GPS machine that you have in your car is in time with the GPS satellite. In just a space of a few days, it can be quite a few yards off. It will tell you that you're in a completely different street to what you're actually in, unless you take into account special relativity. So that's quite a popular example, for lack of a better term. I suppose you're wondering, why is this happening? Why is it that more gravity means slower time? Well, we can think about this quite simply by thinking about space-time, which is the fact that space and time are interconnected. We live in a three-dimensional spatial universe: length, breadth, height. Okay, that's obvious. But everything also has a fourth dimension: duration. So not only do I exist here, I also exist now. Everything that has a gravitational pull pulls at space, which must mean that it also pulls at time. So, very simply, that's space. That's space-time. Right? Point A to point B. If we were to include a mass in the middle of it, that's very heavy, really massive, space-time bends. You can see this if you think of, the popular example is a space table. Upturn a table and stretch, say, I don't know, nylon tights or something across it. Right? Then, drop a cricket ball in the middle of it, and you'll watch as it bends down to accommodate the weight of the ball. That's exactly what's happening when you have a planet, a black hole, a person, anything in space-time. It bends everything. As you can now see here, that distance and that distance are the same. Then going down here, will take longer and will go across that. That's the reason why general relativity works, because it actually bends space. And if it bends space, it must bend time. The other idea, which won't take quite so long to explain, is special relativity. Greater speed, slower time. That's literally it. If you were to run really, really fast, like we're talking about 0.999 the speed of light, time for you would travel a lot slower than it would for the rest of the world. This was tested using an atomic clock, which is just about the most accurate form of timekeeping you can, well, not you can get your hands on, but that exists on our planet. It actually measures the amount of time it takes for an atom to wobble, so it is incredibly accurate. Scientists had two atomic clocks, identical atomic clocks, and both started the time on both of them. One of them was just left in the laboratory. The other one was put into a plane and taken around the world. And when it landed, they realised that even accounting for general relativity, that the clock that had been on the plane had experienced less time than the one that remained stationary. This was because, as the airplane was moving, time was slowing down for it. The reason for this, very quickly, is following an idea of a light clock. We know that light is an absolute constant, 3 times 10 to the 8 meters per second. The amount of time that it takes for light to travel between point A here and point B there, we'll say, can be about 10 seconds or something like that. If our frame of reference, our A and B point, are moving to the side, then the light has to travel like that before it can reflect. This speed here cannot be greater than 3 times 10 to the 8. Which must mean that, because the speed of light must remain constant, time must be going slower. Nothing can exceed the speed of light. Those are the two ways in which you can change your passage of time to the future. How you can make it such that in 2 years you can see 20 years, by moving extremely fast or putting yourself into a gravitational well. I'm not going to tell you about time travel to the past, because we'll be here all night. I shall save that for another speech. I hope you enjoyed that. I hope it wasn't too complicated. And please bear in mind my original version of this was an hour and a half long. So I hope I managed to cut that down nicely for you. Thank you very much. And do we have any questions?
Yeah. So is time travel possible?
Yes. Kind of. Time travel to the future, as I say, that's easy.
Mm-hmm.
And it's entirely possible, and obviously it's being done. It's being done as we speak. This is in fact the reason why I was saying about how you can't really tell how old the universe is, because you've got all these little bits of heaviness in certain places, so some parts of the universe can be younger than others. Insofar as travelling to the past is concerned, there are theories about how it would work, but practically speaking, we can't do it yet. If we wait a few hundred years, we might be able to do something. That would take
so if I want to go forward in time by 20 years,
yeah,
can I do it?
it would be extremely, extremely, extremely expensive, but yes.
How could I do it?
How could you do it?
Yeah.
Interestingly enough, what you can do is that this idea that speed means that you travel forward in time faster. If you're in your little pod,
Yeah.
you experience 2 years and 20 years happens outside. Your pod just has to be rotating at an extremely fast speed for those 2 years. But we are talking astronomical speeds here.
So I would get blown apart.
That's the practical problem here. Yes. An alternative.
I think I'll pass.
Accepting my no.
That's why practically it doesn't work yet. But like I said, in 500 years' time, we don't know. I know that's not now, but that is an option. Yes?
You mentioned quite a few theories for time. Do you subscribe to any of them particularly? Or,
Do I want any of them?
sort of follow anyone particularly over the others, or think that anyone is true compared to others? Quite a few different theories there.
All theories of time travel do kind of make sense. You have to go quite in depth into a lot of them to actually realise that a lot of them say very similar things. I don't really think I can say that there is a favourite method. The idea of wormholes does make sense, because space-time is actually a bit of a mess. Right? There was a Doctor Who thing. I am actually going to quote Doctor Who, yes, where he goes on about wibbly wobbly, timey wimey. That is actually an incredibly good way of describing it, except you have to change it to space-timey wimey. Because space is folded in on itself. Technically, 5 feet that way is Andromeda. Because space is curled in on itself in such a way that 2 minutes that way is a million years away as well. The point here is that it would be possible to travel using a wormhole millions of miles just by passing through the wormhole, which goes simply. That is actually a physical drawing of what it looks like. We're here. We want to go here. We can go the long way around, which is just travelling there, like aiming straight at Andromeda and going. That would take a few thousand years, give or take. Or we can go through a 20-metre wormhole.
Why hasn't anyone done it?
Because we can't find the wormhole. We'd have to find the wormhole, and the point is that we can't actually physically see a wormhole. Our best bet at the moment is that they might be inside black holes, because physics collapses when you get into a black hole because of the sheer amount of gravity.
Don't you worry though that for the same reason, you know, it's all very well you might want to go forward in time, but you get crushed, you get destroyed because you're going around so fast. In a black hole, you probably get mashed up as well.
The official term is spaghettification. It's actually called spaghettification. There's quite a popular image, which some people think is a joke, but it's actually entirely true. Well, you got your black hole here, and you got your little spaceman there. Beautiful drawing, I know.
And you get stretched out.
And you get stretched out and things like that. Because what happens is that because of one of Newton's laws, I can't remember which one. It's not Newton's law. What am I talking about? Because the closer you get to a body, gravity increases to the power of 2. So your feet will be accelerating a hell of a lot faster than your head will be. So you will immediately be stretched out like that.
So you'd immediately die.
Yes.
Before you even got inside the black hole.
The spaghettification is so quick that your bones wouldn't even have time to break.
Sure, it depends what happens at that end.
No, because if you've got destroyed on this side, then you're fucked on the other side.
Pretty much, yeah.
You
can't be squished. Once you get spaghettified, it's pretty permanent. You get stretched.
We could try this out on you, Stuart, if you like. You know, just put you in one of those torture machines that stretches people out, and then you'll be like, no, it's fine. I feel fine.
Sure, you've got continuous time, and it's an infinitesimal amount of time that you're there for. That your body won't notice it, so it won't have time to sort of notice it's all
death
in different places.
Yeah, but you all have died in the meantime.
Yeah. Death is pretty instantaneous. It's not a gradual thing. I'm going, and I'm there. Yeah, it's quite well done.
I don't know, you've had the bullet through someone, or sort of stabbed someone, and then sealed them up really quickly.
They wouldn't die, would they? It'd still be alive, just almost mortally wounded. Did you have a question?
Yeah. Do you think it's ethical to travel through time, either forwards or backwards, because of the problem possible?
Kidding me?
Because of the
Is it
problem.
ethical? Is this a thing of our world? Like, do we have to worry about the ethics of?
Can you let me ask the question?
You know what you're saying.
Is it ethical to go forwards or backwards in time because of the possibility of unintended side effects of accidentally affecting the timeline and thus altering the future?
That is a very, very interesting question. That's actually a good question. So, but I can't explain that now
Okay.
because it's quite chunky, to be honest. On my next speech, I will explain that because that comes into all the idea of paradoxes. One of the ideas, though, I will tell you, is that it's not possible to macroscopically travel through time. Basically means that we ourselves can't travel through time, but other things can, which I will explain a little bit more next time. So, watch this space. Do you have questions as well? No?
If you stop time,
You can't, because matter is unable to travel at the speed of light.
okay, wait a second. Like this big crunch,
Yeah.
why on earth would it happen? Why wouldn't we just carry on going out?
Because it depends. It depends on a constant. I can't remember the name of.
Planck's constant, or is that something else?
No, it's completely different. It's what was it? It's not Hubble's constant, but it's something like Hubble constant. Basically, we have an equation. We don't actually have values for it, and depending on what this one value is, will tell us whether or not the universe is able to sustain to continue expanding, or if it will.
You were saying that if it did crunch,
Yeah,
then time would go backwards.
the cosmological hour time will point backwards. Yes,
So this conversation would happen again,
but backwards.
backwards.
Logically, yes. Scientifically, probably. Because all of the hours, not all of the hours of time have been proven to be connected,
Right.
but most of them have been. One of the long-running problems, I believe, is a connection between the quantum and the thermodynamic hour of time. We're able to find connections for some of them, but some of them don't make sense. I mean, obviously, the thermodynamic hour of time and the causal hour of time with the mug. I use the same analogy because they're linked. Right? Cause, smash, effect, increase entropy. We think some of these hours of time might not be reversible, so that might mean that the universe can't do a big crunch. But we don't know yet. We don't know for certain. There is nothing in physics that disallows time travel completely. And that's a fundamental concept in physics, that if it's not disallowed, we assume it is allowed. Because it just means it's a lot easier to work the numbers. Anything else? Cool, excellent. Thank you very much indeed.